In this video, we will describe what happens in the AM modulation and demodulation part of an AM radio system. Now, AM radio may seem so last century to most of you. It turns out that much of what happens in an AM radio system also applies in almost every other communication system, including modern digital communication systems. These things include modulation to a carrier frequency, demodulation from the carrier frequency, and recovering the information signal from the demodulated waveform. So this may seem out of date, and in a sense it is, but the principles are still useful. So what I have on the screen are some of the components of an AM radio system. We have a microphone that collects speech signals or music or whatever it is you're going to broadcast. The output of this microphone goes to an AM modulator, and the output of the modulator is a signal that gets broadcast by the AM station antenna. And then that signal travels via electromagnetic radiation to the antenna of a radio. So the radio now wants to take this signal that I broadcast and that it's received and get the speech signal or music or whatever back so you can listen to talk radio or whatever it is you're trying to listen to. But other radio stations are also broadcasting signals, and these other signals are also showing up at the antenna. And these signals interfere in some sense with the signal that we want. The tricky bit is how to get the AM radio to select the signal we want from all these other signals. And so the whole point of AM modulation and demodulation is that it allows us to do this. And actually this is the whole point of most modulation and demodulation schemes. It turns out analysis of modulation and demodulation really work best in the frequency domain, because in the frequency domain you can see all the different things that are happening at the modulator and what happens in the radio receiver as well. So we'll spend most of our time looking at what happens in the frequency domain. So let's start with the inside of the AM modulator. We have our information signal coming in. I'll call it M of t. And we'll assume that M of t has been scaled so that its absolute value is always less than 1. And the first thing that happens inside the AM modulator is that we add 1 to M of t. And this makes the resulting signal, that is M of t plus 1, always be positive. So as an example, if I have an M of t that looks something like this over some period of time, after I add 1 to it, that just raises it up by 1, and so I get the same shape, but it's raised by 1, so now it has no negative values. And after we add the 1, we then multiply by cosine omega ct, where omega c is called the carrier frequency. And then this product is output, that's the output of our modulator, and we'll call this x of t. And this signal then goes through a very large power amplifier and is broadcast through the antenna. So if we look at what x of t looks like in the time domain, it basically has an envelope given by the raised up m of t. And so I'll draw that envelope. And x of t wiggles between the two levels of this envelope. So you can see that the amplitude of the cosine waveform now depends on m, and that's why we call it amplitude modulation. Okay, at this point, many of you think I've lied to you. I said we were going to analyze this in the frequency domain because that makes more sense, and yet we have nothing in the frequency domain. So let's go back and look at the frequency domain version of the signals in the modulator. In the frequency domain, we'll look at the magnitude spectrum m of omega, which is the magnitude of the Fourier transform of m of t. Now, we don't know exactly what m of t is or what m of omega is. And so what we'll do is we'll just make a few assumptions that are necessary for the whole thing to work out. We'll require that m of omega fits into the frequencies between 2 pi 5,000 and minus 2 pi 5,000. And the idea is that it's 0, or at least it's negligible outside of these frequencies. In other words, it has a finite bandwidth. Now this is how AM radio actually works and why the sound quality in AM radio is not great. The sound signals, which sound signals often have meaningful information up to about 20 kilohertz, have to be low-pass filtered to fit into a 5 kilohertz bandwidth for AM radio. And we're basically going to use the idea that the bandwidth of M is limited to allow the signal that we want plus the signal from many other radio stations to exist together in such a way that the radio can pick out the station we want. So again, we're not going to assume that we actually know M of t. We're just going to assume that we know that M has a finite bandwidth. Okay, so the time domain operation where we add 1 is equivalent to adding a delta function at the origin of magnitude 1 in the frequency domain. And this delta function will be converted into the carrier part of the transmitted signal when the magic occurs. And this is where the magic occurs. When I multiply m of t plus 1 by cosine omega ct, I am multiplying in the time domain, which means that in the frequency domain I am convolving m of omega plus delta of omega, that's due to the 1, with the Fourier transform of cosine omega ct. You'll remember that the Fourier transform of cosine omega ct looks something like this. It's basically 2 delta functions. So when I take m of omega and convolve it with these delta functions at minus omega c and omega c, I basically get 2 copies of m of omega plus the delta function. One copy is shifted by omega c, and the other copy is shifted by minus omega c. So again, I've taken these 2 copies of the spectrum, and one goes out in a positive direction, the other goes out in the negative direction. This property that multiplying by cosine omega c in the time domain creates 2 copies of my signal in the frequency domain, and they're both shifted out to omega c and minus omega c, is called the modulation property of the Fourier transform, and it gets used in almost every communication system on the planet. So just to make sure we're clear, we're looking at the magnitude spectrum of x of omega. And one of the things that I'm not doing here is looking at the phase spectrum, because we're working conceptually and we're looking at where things get moved around in the frequency domain. Now this works fine conceptually, but if you're doing detailed calculations, you can get yourself into trouble if you forget that these Fourier transforms all have a phase spectrum as well as a magnitude spectrum. Okay, so the last thing to point out is that the modulated spectrum, that is x of omega, fits between omega c minus 2 pi times 5 kilohertz and omega c plus 2 pi times 5 kilohertz. Now we know what the spectrum of the output of the AM modulator looks like. It's this messy thing here. Okay, so this is the spectrum of the signal that gets broadcast. Now we want to turn our attention to the radio receiver. We want to understand how the receiver separates the signal we want from all the signals from the stations that we don't want. I've drawn a block diagram of how the AM radio receiver does this. And we'll go through this block diagram in the same order that the received radio signals go through it. So the first thing in the block diagram is the radio antenna. This receives radio signals, and it's connected to what's called the RF amplifier. RF stands for radio frequency. The RF amplifier is an amplifier that's also a tunable bandpass filter. The output of the RF amplifier goes into a mixer, and the output of the mixer goes through a bandpass filter and then into the demodulator. The output of the demodulator is the sound I want to listen to. So we'll go through each of these steps and look at what's happening in the frequency domain. So let's first look at the frequency domain representation of what's coming in from the antenna. And I've labeled this point A in the system. Okay, so in the frequency domain, out here at omega c is the information that I want, and this is also at minus omega c. But I also have all these signals from the other radio stations that are broadcasting and that my antenna picks up. The issue is that I don't want to listen to all this other stuff. I want to listen to the one station that I tuned into, and that's at omega c. So this brings us to the next step. If we go back to our diagram of the AM receiver, the RF amplifier takes the signals coming in from the antenna, and these signals can be very small sometimes, millivolts or less, and it amplifies them. And also it's a tunable bandpass filter, so it starts to attenuate the signals from the stations that I don't want. Attenuate means to be made smaller in magnitude. Okay, so this shows the magnitude of the frequency response of the tunable bandpass filter. You can see that the pass band is at omega c, and as we get farther away from omega c, the frequency response gets smaller and smaller. So this means that signals with frequencies where the frequency response is small will be attenuated. So this bandpass filter does get rid of frequencies that are not at omega c, but it doesn't do it very effectively. The reason for this is that it's tunable, and so you can change the center of the passband to the frequency of the station you want to listen to. It's quite difficult and somewhat expensive to create a filter that is both tunable and has a very sharp cutoff frequency. So especially if you're building a cheap AM radio, you don't want to do it that way. And so in the RF amplifier, we opt for tunable, and we'll clean up the spectrum later. So I'll label the output of the RF amplifier with B. And this is right here on the AM radio. And this output is the product of the spectrum going in to the RF amplifier and the frequency response of the RF amplifier. So you can see that the station I want comes through this filter pretty much unchanged. The other stations, these ones that I'm not interested in, are multiplied by parts of the frequency response to the filter that are small. And so I get stuff that looks like this. Now, because my bandpass filter does not have a sharp cutoff at the edges of the passband, these guys are still pretty significant. They're not gone, and they're the junk we don't want to listen to. They'll get cleaned up later. At the output of my RF amplifier, I have something that looks like this magnitude spectrum labeled B. So now we need to look at what happens in the mixer. The mixer multiplies the signal at B by cosine omega LO t. Omega LO is the frequency of a local oscillator, and it's equal to omega c minus omega IF. Omega IF is called the intermediate frequency, and in AM radios this is typically 455 kilohertz. This intermediate frequency is different in different types of receivers. So for example, in FM radios or analog television, which doesn't really exist anymore, or other receivers, you'll have a different intermediate frequency. In practice, this is typically set to be what's necessary to make the design work well. So let's go back to the frequency domain and see what happens in the mixer. We are multiplying by a cosine in the time domain, which means that we are convolving with the transform, the Fourier transform of the cosine in the frequency domain. The Fourier transform of the cosine is just a delta function at omega LO and another delta function at minus omega LO. So we are convolving the waveform at B with these two shifted delta functions. And this just takes the waveform at B and makes a shifted copy that is shifted up in frequency by omega LO. So the origin is shifted up to omega LO, and another copy where the origin is shifted down to minus omega LO. So I get a copy of the stuff at omega c that I want moved up in frequency, and a copy moved down in frequency. The same thing happens with the stuff at minus omega c that I want. So what does this look like when we're done? When I copy and shift up, I have a copy of the station at omega c plus omega LO, and another at minus omega c plus or minus LO, and all the garbage that I don't want follows them around from this garbage from the other stations. When I copy and shift down, I have a copy of the station at omega c minus omega LO, and another at minus omega c minus omega LO, and I still have all the junk following these guys. So by using the mixer, I have the signal that I want at omega c minus omega LO, which is actually omega IF, and I have the same thing at minus omega IF. So now I have the signal that I'm trying to isolate, the one that I want to be able to reconstruct at this intermediate frequency. So now I know what the signal looks like at point C. It's got the radio signal that I want at the intermediate frequency, and then all the junk, the stuff that I don't want, that's followed us around. To get rid of the junk, we now use the final bandpass filter. This filter has a sharp cutoff at the edges of its passband. It has a transfer function that looks something like this. When I run the output of the mixer through this filter, the only thing that remains is the radio station that I'm interested in at omega IF and minus omega IF. Everything else has been attenuated to the point where it's negligible, and that's the miraculous part of it. Now I have only the signal I want at a particular frequency, and the only thing that is left for me to do is to reconstruct the signal, which is to take it from the intermediate frequency back to the original frequency band, and that original frequency band is oftentimes called baseband. So I've neatly redrawn the voltage input to the demodulator, which is the signal at the output of the bandpass filter, and I've called it V sub D. The demodulator will recover the original signal M of T from V sub D. Now, I've shown this in both the frequency domain and the time domain. The reason for that is that there's conceptually at least two different ways to get the original signal back. And the one that's linear is best understood in the frequency domain. So the linear way involves moving the signal in the frequency domain by multiplying it by a cosine and then low-pass filtering it. So I've written my cosine with a phase term, theta, and I'll explain why in just a minute. The output of the low-pass filter is 1 plus m of t. Removing the 1 is pretty easy with a level shifting circuit. So multiplying by a cosine, as we've already learned, makes copies and shifts them in frequency. I end up with the bumps at the origin that contain my signal. And then I use the low-pass filter to remove the unwanted frequencies at 2 omega IF and minus 2 omega IF, and that gives me the signal I was trying to get. Now, I have sort of cheated. To really make this work, I need to know the phase of the sinusoidal part of V sub D, because my cosine omega IFT has to have that same phase. Estimating this phase used to be expensive and difficult. Today, you can buy relatively cheap integrated circuits called phase-locked loops that can do this. The cheaper alternative, which is used in AM radio, is nonlinear, so it can't be analyzed easily in the frequency domain. So to show this, this is our signal in the time domain. Conceptually, at least, this signal is the input to this circuit, which consists of a diode, a capacitor, and a resistor. The input is V sub D of t, and the output is the voltage across the resistor. If you are unfamiliar with the diode, it acts like a switch, and whether the switch is open or closed is controlled by the voltage across the diode. When the voltage across the diode is positive, it's like a closed switch, which allows current to flow. When the voltage across the diode is negative, it acts like an open switch, so that just the resistor and capacitor working together cause things to happen. No current is flowing through the diode. The diode acts like a half-wave rectifier. So conceptually, what this means is that it chops off the negative part of the signal and just throws it away. And the positive part gets fed into the resistor-capacitor combination, which is a low-pass filter. This low-pass filter gets rid of the wiggly bits, so that's the sinusoid with frequency omega IF, and leaves us with the magnitude of 1 plus m of t. To give you just a little bit more detail about how this circuit works, suppose that at a particular point in time I have this waveform as V sub D of t. As long as the input voltage is larger than the capacitor voltage, the diode acts like a closed switch and the capacitor charges up as V sub D increases. So if the red represents the capacitor voltage, it goes up until it gets to the point at the peak of the waveform. Then V sub D starts to go down, which means that the capacitor voltage will be higher than V sub D, so the diode shuts off, that is, the switch opens, and the capacitor will start to discharge through the resistor. The resistance and capacitance values affect how quickly this discharges. Once V sub D is higher again, the diode turns on and the capacitor charges up. You can see that what this circuit does is connect the peaks of the waveform. So in the time domain, this is fairly easy to understand. In the frequency domain, this is an absolute mess, and it's very difficult to analyze. So hopefully this has all made sense. At this point, we'll conclude this video. Thanks for watching.